Okay, let's go ahead and get started. So just one administrative announcement. There was one non-trivial typo on the problem set. There's a phi bar that should be a phi in my definition of spatial parity operator. I'm sure there are other typos. The other typos are there for your entertainment, amusement. This one is a non-trivial one. So hopefully that won't get you mixed up. Okay, so today what I wanted to do is conclude our discussion of scalar quantum electrodynamics. Which is, I would say, maybe our first full-fledged, really interesting quantum field theory that we've studied in this class. So just to remind you, this is a theory where we have a gauge field given by some four-vector field, which is a four-vector A mu, along with a complex scalar field phi that could describe electron and positron states in the approximation where we neglect the spin of the electron. And in the free theory, that is to say in the limit where the electric charge is very small so that the electrons and positrons don't interact with the photons, we can just expand everything in terms of raising and lowering operators as usual, and the operator phi is the operator which creates an electron, or sorry, creates a positron or destroys an electron. So here, A dagger is the operator that creates an electron, B dagger is the operator that creates a positron, and there's some similar expression for phi bar, where now you have an AP dagger here and a BP here. So phi bar is the operator that creates an electron or destroys a positron. And likewise, in the free theory, we can expand our gauge field A mu in a similar way. So we'll expand it in terms of Fock space operators. So there's some normalizations there. And the only subtlety being that we need to keep track of the fact that there are two different polarizations of the photon that I've called epsilon 1 and epsilon 2 here. I've labeled them by an index I that runs from 1 up to 2. And here, the epsilons are some polarization vectors. And exactly which polarizations you choose, first of all, depends on your gauge choice. And also, it's just a choice in how you wish to label the polarization states of a photon. So, for example, typically, we're going to use plane wave polarization vectors so that, for example, if your momentum of your photon is purely in the z direction, so that p mu is E, 0, 0, E, then we would take epsilon 1 to be pointing in the x direction, and epsilon 2 to be pointing in the y direction. But of course, there are other sorts of choices we could make. For example, we could consider circularly polarized bases or something else. The important point being, however, that the photon is massless, so that p squared is equal to 0. And as you can see from this expression, the polarization vectors are orthogonal to the direction of propagation. Okay. So a photon or an electromagnetic wave has polarizations only transverse to the direction of the propagation of the photon. Okay. That's something that hopefully is more or less familiar to you from electromagnetism. And from these from these expressions for phi and A, in terms of the raising and lowering operators, one can compute the propagators. which allow you to compute, for example, all of the correlation functions in the free theory. So the propagators, there are two of them. There's a propagator for the phi field, which is just the propagator for a real scalar field. The only difference being that I've had to mark up this propagator to put an arrow on it. That arrow tells you what direction charge is flowing. So in this case, charge is flowing from the right to the, or maybe left to the right. I can never quite get it straight. Left to the right here. So for example, there would be a phi operator over here and a phi bar operator over there. And likewise, there's a propagator for the photon, which we derived last class. Now the photon has an index mu, which means that you need to label the endpoints of the propagator with an index. And the actual form for the propagator, we found, depends on your gauge choice. So in particular, we introduced a family of gauges known as the R-psi gauges. And the propagator in this family of gauges will depend on the momentum of the photon, as in the case of a scalar field. But it also depends on this additional parameter psi, which just encapsulates your dependence of the propagator on the choice of gauge. Okay. So very often we'll set psi equals to 1. That's Feynman gauge. But there are other times when it might be useful to take other values of psi. Okay. And the fact, and it's a fact which we will prove today under some limited circumstances, is that the result of any computation is going to be independent of our choice of gauge, and thus should be independent of this parameter. Okay. Now, this is something that is far from obvious, and I'm not going to give you a completely rigorous proof today, but rather give you some examples of why it's true and some of its implications, and so then hopefully you'll believe it from there. Although it is, of course, something that one could prove rigorously. Okay. Now, in addition to these free propagators, we also have interactions. So there were terms in the Lagrangian that describe the interaction of a photon with an electron and a positron. So these lead to vertices that look like this. So here, because there's one free photon leg here, there's one index mu, one free index mu, and the value of this interaction vertex, well, as usual, is proportional to the coupling constant. So it's proportional to the electric charge, which tells you about the strength of coupling of electrons and photons to, of electrons and positrons to the gauge field. And in order to soak up that index, there have to be some powers of the momentum there. That comes from the fact that there's a derivative here in the interaction. Okay. And here, P1 is one of the momenta coming in, and P2 is the other momentum. And here I've oriented things so that the momenta are in the direction of particle flow. But if I changed the orientation of my momenta, I would get minus signs here. Okay. So we'll have to keep track of whether the momenta we're talking about are in the direction of or opposite to the direction of particle flow. And there's one final interaction vertex, which describes two photons interacting with an electron and a positron. So this leads to a quartic vertex with two free indices. Which is just equal to the coupling constant times g mu nu. Okay. That g mu nu is because I can write this as a nu, g mu nu. Okay. By the way, last time I told you this is called the seagull diagram, but it didn't look much like a seagull to me. So I actually asked someone about this. Apparently, sometimes people draw it like this. Okay. Then it's supposed to be like, this is supposed to be water down here, and this is supposed to be a seagull here. Okay. So it looks a little bit more like a seagull. Still not so much like a seagull, but maybe a little bit like a seagull. Okay. Okay. So let me just, so there are also a few other rules that we're going to need to keep track of when we start writing down Feynman diagrams in scalar QED and later on in full-fledged real QED. So the first rule that we have to remember is charge conservation. So charge conservation, otherwise the fact that the action is real, implies that when you connect up Feynman diagrams, when you connect up these vertices and propagators in order to draw a Feynman diagram, the particle flow arrows must connect up. Okay. That's just saying that each interaction individually in the Feynman rules will conserve charge, just like it conserves momentum. Okay. And another piece of notation that we will use is that just in order to not have to draw separately particle flow arrows and momentum flow arrows, we'll always take our momenta to flow from left to right. So momentas point from left to right. Okay. So I won't bother, if I draw a diagram like this, I have to draw the particle flow arrows, but I could put, say, momenta P and Q there, and you automatically know that those momenta point like that and like that. Now, in the present diagram, if that were just the only thing we were considering, it's not too important. But remember that when we have these interaction vertices like here, like this one, the relative orientation of the particle flow arrow and the momentum arrow is important for determining certain signs. Okay. The final thing that we need to remember is how we go about connecting this up and calculating scattering amplitudes for physical states. So the physical states of a photon don't have a free index. Instead, they have a polarization. Okay. And the rule that we need to remember is that to describe interactions for external photons, with polarizations, say epsilon mu, then you just write down the corresponding Feynman diagram. There'll be one free index if you have one free photon, and you just contract that with the corresponding polarization vector. So, for example, if you have some electron going along here, and you want to calculate the amplitude for it to emit a photon, this is called a Bremsstrahlung process, then this will be some amplitude, okay, with some free index mu, and then the amplitude for that photon to be emitted with a particular polarization would be the polarization tensor epsilon contracted with mu, with m mu. The only slight subtlety we need to remember is that occasionally you might want to work with polarization vectors that are complex. Okay? So for the polarization vectors that are linearly polarized, they're just real. But if you want to work with circular polarization, then you might want to introduce complex polarization vectors. And in that case, for an incoming photon, we contract with epsilon, the polarization of the photon. And for an outgoing photon, you contract with the complex conjugate of epsilon. Okay. And the reason for that is that when we expand in terms of the Fock space operators, if epsilon is complex, we really have an epsilon star here rather than an epsilon, because the gauge field is real, so that the lowering operators here are multiplied by epsilons and the raisings by epsilon stars. Or, of course, you could do it the other way around, the point being that they have to be complex conjugates of one another. Okay, so this is just a sort of lightning review of what we described last time. And again, just to remind you, although we haven't been doing too many loop diagrams yet in this course, because loop diagrams get complicated and sort of there are lots of thorny conceptual issues that arrive when we consider loop diagrams. But as with scalar field theory, I just want to emphasize that in diagrams with, say, L loops, just as in the scalar case, there will be L undetermined momenta after we enforce momentum conservation at each vertex. The momenta, these internal particles that are not observed that appear in loops, are virtual particles. And the momenta should be integrated over. And in particular, the four momenta should be integrated over. So if L is the momenta of one of these undetermined momenta, then you integrate d4L. And the important point is, just as in the case of a real scalar field, what you don't do is enforce the equations of motion. Okay? So you don't enforce, say, L squared equals 0 for a photon, or L squared equals m squared for an electron. I'm using here the shorthand that gamma stands for photon. Okay, I guess you guys have probably seen that before. If not, you're seeing it now. Congratulations. Are there any questions before I continue? So, for example, if you want to calculate, say, some contribution to the electron propagator, I guess I'm getting ahead of myself. If you want to calculate some contribution to the electron propagator, then you would integrate over the four momenta that's running around in that loop there. Okay? And in particular, that photon does not have to be traveling at the speed of light. Okay? It's a virtual photon. It could be, traveling, L squared could be any number, and it will be integrated over. I mean, this is the basic idea of quantum mechanics, that virtual paths in the path integral that you integrate over don't solve the classical equations of motion. Are there any questions before we continue? So what I want to do today basically is I want to just do a bunch of computations in scalar QED, just so that we get a little familiar with this. We'll see some differences with real scalar fields. We'll also see some new features that are arising having to do with gauge invariance that are new. And so we'll get a sort of feel for how to do computations in scalar QED. So that starting next class, when we move on to real QED, we'll at least have a feeling for some of the complexities that arise. There's a question. Yeah.
Do you think the timing diagrams is describing different physical processes that occur?
Yes. Okay. You both think of them as as contributions to a perturbative expansion in to some correlation function or a scattering process. But you should also really think of them as physical processes that occur. Okay? I mean, there are a lot of subtleties that happen when you think of them that way, because the important point is that the virtual particles are not observed. Okay? And so because they're not observed, that's the definition of a virtual particle, it's not observed. So because they're not observed, to some extent the question of whether you should think of them as physical processes is not a physical question. Okay? And so to some extent it's not a question you should ask. Okay? As we're going to see today, there are many cases where there are physical principles that have to be true that only arise, that only happen to be true when you add up many different Feynman diagrams and get cancellations. Okay? So if you think of each individual Feynman diagram as a physical process that must happen, then you can easily mislead yourself. Okay? I hope that's sort of an answer to your question. Yeah. I mean, to some extent, you know, Feynman's famous motto is just shut up and calculate, right? Okay, so to some extent that applies here. And I guess, yeah, I mean, I would say the whole point of virtual particles is that you don't observe them. So there's an extent to which it's a fiction, but of course it's an incredibly useful fiction. And of course, I mean, as we'll see many times in this course, there are deep relationships between loop processes which involving unobservable virtual particles and tree-level processes involving particles that you can see. We'll see that hopefully by the end of class today. Good. Any other questions? Okay. So let's do a couple examples. So let's do what's known as Moeller scattering, which is the scattering of two electrons off of each other in quantum electrodynamics. Okay? Actually, I'm never quite sure how to pronounce, that's an O with a slash through it. I'm never quite sure how to pronounce it, Moeller scattering or something like that. Okay. So now, of course, if the electric charge is set equal to 0 and we're in a free theory, then this is trivial. This is just computed by Wick's theorem. What we'd like to do is compute the first non-trivial contributions to this, where two electrons will interact with one another by the exchange of a photon. Okay. So in particular, here we have an electron that comes in with momentum p1 and leaves with momentum p3. Another electron that comes in with momentum p2, leaves with momentum p4. And then enforcing momentum conservation, the photon that is exchanged between them must have momentum p3 minus p1. So we can go ahead and let's just go ahead and write down what this amplitude is using our Feynman rules. So when we were studying 2-to-2 scattering, we actually saw that for the real scalar field, there were three different kinds of diagrams that one could write down. There was the S channel diagram, the T channel diagram, and the U channel diagram. This is the one that we call the T channel diagram. Okay. And it's easy enough to write down. So you have this interaction vertex. There's first that interaction vertex on the top. And then you have a P1 mu plus P3 mu. That's the interaction vertex right here. Then you have the propagator. So that gives you a G mu nu. Now, for right now, let's not make a gauge choice and check that the answer that we get is independent of our choice of gauge at the end of the day. So here's, I guess I call that K. Here's the R psi gauge term, written in arbitrary gauge. And so this is the propagator. As usual for a tree level diagram, I can forget about all of the I epsilons. Those are only going to be important when performing loop integrals. And then we have the interaction vertex down here, which gives me a minus IE times P2 mu plus P4 mu. Sorry, nu. So here, mu is the label up here, and nu is the label down here. And as usual, when you hook up these different interaction vertices and propagators with one another, you contract the various indices. Yes, question?
No, here P squared is not 0, right? Because it's an internal part. So,
Yes. So here, K is P3 minus P1. Okay. So K squared is P3 minus P1 squared, which is what we call T in our Mandelstam variables. So the first thing that we should notice is that let's just look at what happens when we contract this term here with that K over here. So you get a P1 plus P3 contracted with K, which is P3 minus P1. So what is that? That's P3 squared minus P1 squared. All of the external states have P squared equals to M squared. M is the mass of the electron. So this is M squared minus M squared, which is equal to 0. So what does that mean? That means that this term over here is just equal to 0, and the result is independent of the parameter psi as I promised you it would be. Okay. So this is a very simple example. And we see that this diagram just gives you E squared times, now we just have this metric term here, so we get P1 plus P3 contracted with P2 plus P4 divided by T, that Mandelstam variable. Okay, so that was the T-channel diagram. Any questions on that? It's now easy enough to write down the U-channel diagram. So what's the U-channel diagram? The U-channel diagram, remember, is the one where you interchange the 3 and the particles 3 and particle 4, which actually is the same as interchanging particles 1 and particle 2. You can see here that I've been careful to make sure that all of my arrows connect up so that charge is conserved on each vertex. So whereas the T-channel diagram described an electron coming in with momentum P1 and leaving with momentum P3 and interchanging a photon with something that came in with P2 and left with P4, here I'm interchanging the role of P3 and P4, really reflects the fact that these electrons are identical particles, and you really can't tell of the initial and final electrons, which you can't match up which of the initial electrons was which one of the final electrons. The answer for M sub u is the same as M sub t, except with P3 and P4 interchanged. So that's E squared now over U. Remember where U is the Mandelstam variable P1 minus P4 squared. And you get a P1 plus P4 contracted with a P2 plus P3. So that was the U and the T channel diagrams. Can anyone tell me what the S channel diagram is? to see if you're all awake. So the S-channel diagram doesn't exist, right? Because the rule is that you have to have an arrow coming in and an arrow going out. If the S-channel diagram existed, it would be possible for a photon or for a particle to come in, and create an electron-electron pair or a positron-positron pair. Okay. So the S-channel diagram does not exist. So unlike the case of the real scalar field, there's no symmetry between ST and U. Okay? The 2-to-2 scattering for the real scalar field, you had this STU symmetry, that's not present in the present case because of charge conservation. So now, if you wanted to go ahead and do it, you could go ahead and compute the scattering cross-section. Which is literally the probability that these two electrons will scatter off of one another into some solid angle omega. So this is the total amplitude, let's call it mu plus mt squared, divided by the center of mass energy, times some numerical factor, which happens to be 64 pi squared. I didn't compute that. I looked it up. I recommend that if you have to do this computation in the future, you look it up as well. This is one of those kinematic factors involving all those pi's and stuff like that that we worked out when we studied decay processes and scattering amplitudes. So the first thing to notice is that this goes like e to the fourth. Okay. So that's e to the fourth divided by some numerical constant, which is 64 pi squared. The center of mass energy, what is the center of mass energy? That's P1 plus P2 quantity squared, which is what we called the Mandelstam variable S. And then we have a P1 plus P3 contracted with P2 plus P4 divided by T, then plus P1 plus P4 contracted with P2 plus P3 divided by U, all quantity squared. Okay. I haven't bothered to write out the mu's there. I'm just using dots because I'm lazy. Okay. So if you want to, you could go ahead and write this all out in terms of the Mandelstam variables. So for example, as we saw earlier, all of the various kinematic invariants for 2-to-2 scattering can be written in terms of Mandelstam variables. So it's easy enough to check. So what is this? This is P1, P2 plus P1, P4 plus P3, P2 plus P3, P4 divided by T, which is the same as, let's see, S minus U over T. S is P1 plus P2. U is P1 minus P4 squared. So when you square those, you expand them out, you get some m squareds, and you get P1 dot P2, which is the same as P3 dot P4 in S, and similar terms with U. Okay. So you get some completely explicit answer in terms of these Mandelstam variables. So there's a bit of convention that we often use. So we often introduce what's known as the fine structure constant, which is e squared over 4 pi, which is a little less than 1%. And we conclude that the scattering cross-section is proportional to the square of the fine structure constant, so it's something that's typically quite small, times some rather simple function of these various kinematic invariants. So this is the simplest example of the sort of scattering process that we're going to be considering in QED. And it describes the probability that electrons will scatter off of one another because of the interactions, the exchange of a photon into some particular solid angle. Now, I haven't used angles here when I wrote it out. I used the Mandelstam variables because they make life much simpler, as we saw when considering 2-to-2 scattering. But if you wanted to, you could use the results of your problem set last week to turn this into an expression involving, for example, the center of mass energy of particle P1 and the relative angle of scattering. Are there any questions before I continue? Okay. So this was just a simple example. I want to do another very simple example, but the next example I want to do is going to illustrate a kind of interesting and deep principle of theories with gauge symmetries that we're going to come back and revisit again and again throughout this course. Okay. So in particular, what I'd like to now do is consider scattering processes which have external photons. And before I do this, before I actually start computing things, what I'd like to ask is what consequence gauge invariance has for these various scattering processes. Okay. In particular, remember that we now have an external field A. But A is not a physically observable quantity. The only thing that's physically observable are things like the electric and magnetic field, which are invariant under gauge transformations. Okay. So what consequence will that have when we compute scattering amplitudes? So the thing to notice is really that when we quantized the electromagnetic field, we expanded in terms of these polarization vectors, epsilon. So a gauge transformation of A will lead to some sort of change in these polarizations, epsilon. And what must be the case if the theory is gauge invariant is that when you actually compute scattering amplitudes with external photons, the result should be independent of those parts of the polarization vectors epsilon that depend on your gauge choice. So just to make that more explicit, remember that under a gauge transformation, A mu is shifted by the total derivative of your gauge parameter in position space, and in momentum space, this means that if you wrote A in momentum space, you looked at the Fourier transform, you would be shifting it by something proportional to k mu. And the thing multiplying k mu could be arbitrary. It's basically the Fourier transform of your gauge parameter. So what this means is that under a gauge transformation, the polarization vectors, which are the components of the gauge field when you expand in terms of a basis of solutions to the equations of motion, will shift by something proportional to k mu. So the first thing to notice is that in, for example, that gauge that we wrote down above, epsilon mu contracted with k mu is equal to 0. K mu for an external photon squares to 0. So this gauge transformation preserves the condition that epsilon is perpendicular to the direction of propagation. So just to be very explicit, so for example, if epsilon pointed, if you had a photon that was moving in the z direction and it was polarized in the x direction, then you would just be picking up some constant times something proportional to the momentum vector of the photon in the z direction. Okay. And if you want, you could explicitly work out a gauge transformation that would do exactly this. It's easy enough to work out. If you're not convinced by this, I invite you to do so. Okay. So what does this mean? Okay. So let's consider some process with an external photon so that we have some sort of scattering amplitude with a free index. Okay. And what we're supposed to do then is contract that index with the polarization vector of that photon, that external photon. Okay. Now, this could be some scattering amplitude where we also have a bunch of electrons and positrons coming out. We could also have a bunch of other photons coming out. Okay. So there could be other indices as well that describe the other external photons. Okay. But let's just focus on one of those indices for now. Okay. Then we know that because our theory should be gauge invariant, that the answer should be independent of this shift of epsilon by something proportional to k. And this will only be true if k contracted with your amplitude is equal to 0. And this is true for all external photons. So this is a very important feature of scattering in theories with symmetries, theories with gauge symmetries. It's known as the Ward identity. And the remarkable and important thing is that it's something that must be true in order for the theory to be gauge invariant, but it's also something that's not at all obvious from our description of the theory in terms of Feynman diagrams. So we've developed some systematic way of calculating scattering amplitudes in terms of Feynman diagrams. We believe that this rule should be true, but we haven't proven that it's true. Okay. So one can actually go through and give a proof, sort of algorithmically by studying Feynman diagrams and all of that stuff, that indeed these Ward identities are true. I'm not going to go through and do that proof. It's actually harder to do in scalar quantum electrodynamics than in real quantum electrodynamics, in part because in scalar QED you have both 3-point interactions and 4-point interactions. Instead, what I'd like to do is just do a sample calculation where you can check for yourselves precisely that this is true. And then along the way, this will also imply some nice things about why gauge theory diagrams which have internal loops will be gauge invariant. Okay. So there was a question in the back? Yes. Okay. So the argument is that under a gauge transformation, A, in momentum space, A goes to A plus K, the 4-vector K. So that means epsilon goes to epsilon plus K. Now, times some other function of K, but that other function of K depends on lambda. Lambda's arbitrary. So in order for your scattering result at the end of the day to be gauge independent, to not depend on this choice of the function lambda, then K contracted with your amplitude mu has to be 0. Because remember, epsilon mu, m mu is the scattering amplitude for some process with an external photon with polarization epsilon. If you're allowed to shift epsilon by k and the answer can't change, that means that k contracted with m just has to be 0. So, there's a couple different ways of demonstrating this rigorously. From the path integral point of view, it's actually really pretty easy, sort of making a formal argument. The basic idea, if you want to prove this from a path integral point of view, is that all of these scattering amplitudes are derived by considering a generating functional, z of j. J here is now something that couples to a mu, so it's really z of j where j is a conserved current. Okay? And so then if you use the conservation law for the current, that will lead to this result for the scattering amplitude. I don't want to get too obsessed with proving things rigorously, because that way lies madness in quantum field theory. Instead, what I want to do is just give you an example of how this works. You'll actually see that one of the really interesting things is that this is something that requires a cancellation among many different diagrams in order to be true. So this is a more general lesson to keep in mind, which is that Feynman diagrams are useful, but they're not always the most physical way of organizing our information about quantum field theory. Okay? So for example, individual Feynman diagrams that can contribute to a scattering amplitude will not individually be gauge invariant. They'll only be gauge invariant when you sum them all up. Okay? And so we'll consider a very simple example of this. Okay? But the important point is that this is true not for individual diagrams, but only when we sum them up. Fortunately, what you don't have to do is sum up all orders in perturbation theory. The reason being that the theory should be gauge invariant for any value of the electric charge, and you can continuously tune the electric charge, and the theory should be gauge invariant. That means that order by order in the coupling constant, as long as you keep track of all of the terms with a given order in the coupling constant, up to some desired order in the coupling, that quantity on its own should obey the Ward identity and be gauge invariant. Good. Any other questions? Okay. So the process that I would like to consider is, yes?
So in a particular order, but basically we have, for example, one diagram.
If there's only one diagram at a given order, then that'll obey the Ward identity. Okay. But if there are 10,000 diagrams, you're going to need to sum them all up. Okay.
So the order is the important thing.
That's right. That's right. And we'll see explicitly how that happens. Okay. Good. So let me give you an example. Let's imagine that we have an electron and a positron which combine to make a pair of photons. So the sorts of diagrams that will arise are very similar. Oops, sorry, I can't draw a diagram. The sorts of diagrams that will arise are very similar to the ones that we considered before, except now, because the three-point interaction involves an electron, a positron, and a photon, the exchanged particle has to be a positron or an electron rather than a photon. And you can see that then, because the arrows all have to line up, we have to have, the arrow over here points to the left, and the arrow over here points to the right, which means we have an ingoing electron and a positron, okay, rather than, say, two electrons. So let's just give names to all of the various momenta. And so this internal momenta is going to be P1 minus P3. And so this diagram, which again we'll call the T-channel diagram, well, you get two powers of the electric charge from these interaction vertices. From the top one, what do you get? Well, you get the P1 momentum plus P1 minus P3. So that's 2 P1 minus P3. Here, mu is the index up here, and nu is the index here. You know, actually what I'm going to do is let's, just to get used to this, write this all out in terms of polarizations. So let's say that this external photon has polarization epsilon 3, and this one has polarization epsilon 4, where those are 4 vectors. So then this top interaction vertex gave you 2 P1 mu minus P3, using the fact that anytime the momenta flows in the direction of particle flow, you had a plus sign for the momenta. So here, I guess I'm taking the momentum to flow down here. Okay. So usually our notation is that momentum flows from left to right. For something that I draw completely vertical, that is ambiguous. So, you know, I need to be a little careful. But it flows down here because it's P1 minus P3. And then the second one, well, I could use the fact that this is also P4 minus P2 to write this as P4 nu minus 2 P2 nu. Okay. Of course, I could also write it in terms of P1, P3, and P2, but I'll just write it in terms of P2 and P4 for reasons that may become obvious soon. And then we have to divide by the propagator, which is P1 minus P3 squared minus m squared. And then we have to contract with the appropriate epsilon tensors. So there's an epsilon mu 3 and an epsilon nu 4. And I suppose if they're outgoing photons, I should really complex conjugate those epsilons. But let's just choose to work in a basis where the epsilons are all real. Okay. So let's say a linearly polarized basis rather than circularly polarized. Okay, so I can go ahead and simplify this. But actually what I'm going to do is I'm going to simplify this, but I'm going to do something rather sneaky. Okay. So in principle, I could use, so one of the things that I want to use is the fact that, say, P1 squared is equal to m squared, and so is P2 squared, because those are external electrons, so they're on shell. But I'm going to be sort of sneaky, and I'm not going to use the on-shell conditions for the photons. So what I'm not going to use is the fact that, say, P3 squared or P4 squared is equal to 0. Nor am I going to use the fact that P3 dotted with epsilon 3 or P4 dotted with epsilon 4 is equal to 0. Because what I want to do is I want to demonstrate that this Ward identity holds. But in fact, it will turn out that the Ward identity holds even when the momentum Kmu that you're contracting this diagram with is off shell. Okay. And this will be useful if you want to prove gauge invariance. Okay. So I'm just gonna not use those identities even though they're true for the moment, because it'll allow me to prove something sort of elegant a little later on in the lecture. Okay, so we can go ahead and use at least these equations to simplify just a little bit. So you get an E squared out front, and then the numerator here, I can write that as P3 dot epsilon 3, okay, otherwise known as 0, but I'm not going to use the fact that it's 0, minus twice P1 dot epsilon 3. Okay. And then, I've pulled out a minus sign here that comes from, I've used the minus sign that comes from squaring this guy. Okay, okay, I'm sorry, because it's squared, right? Because there are two interaction vertices. And then the other term is a P4 dot epsilon 4 minus 2 P2 dot epsilon 3. Okay, oops. yeah, sorry. It's a P4 dot epsilon 4 and a P2 dot epsilon 4. No, sorry. P4 dot epsilon 3. And a, no, I'm sorry. P4 dot epsilon 4. Sorry, it's the end of a day. And P2 dot epsilon 4. Okay. Divided by, well, I have P1 squared plus P3 squared minus 2 P1 dot P2. P1 squared is equal to M squared, so I can just write that denominator as P3 squared minus 2 P1 dot P3. Okay. Everyone with me so far? Okay. And similarly, there's a U-channel diagram which is the same diagram, except, sorry, I guess those are squiggly lines. It's sort of hard to tell that they're hopping over one another, but they are. So that's the same diagram, except where the two lines hop over one another, so we exchange the two external photons. So that is just the same thing as MT with 3 going to 4, or alternatively, you could say 1 going to 2. That's the same thing. So we can just go ahead and write that down just by comparing with the expression for MT. So we get a P3 dot epsilon 3. So let's first look at this term. You get a P3 dot epsilon 3 minus 2 P2 dot epsilon 3. The first term is a P4 dot epsilon 4 minus 2 P1 dot epsilon 4. And in the denominator, well, I could write that as P4 squared minus 2 P1 P4, but instead I'm going to write that as P3 squared minus 2 P2 dot P3. Using the fact that I could have either exchanged 1 and 2 in this denominator, or I could have exchanged 3 and 4. Okay. Now, the claim that I made was that K mu, M mu, should be equal to 0. And in particular, let's say that we take the photon 3 as our external photon. So in particular, this means that if we set epsilon 3 equals to P3, then the total amplitude should be 0. So let's go ahead and add up mu and mt, setting epsilon 3 equals to P3. So is it clear what we're doing here? Maybe I should see. Is everyone with me so far?
Is it epsilon that's supposed to be unifying?
Yes. Okay. So, I mean, what I really mean is if you replaced epsilon by epsilon plus p, then the diagram should be unchanged. So if you just formally think of epsilon being proportional to P3, then that diagram should be 0. Do you see what I'm saying here? Is that clear? I mean, there's going to be some non-zero part of this, which would, if epsilon z is physical and has epsilon squared equals to 1. But if you added to that something that's squared to 0 and is proportional to P3, you should get 0. So I can just so to check the Ward identity, I just set epsilon 3 equals to P3, and I see if what I get is 0. Good. So let's write down what MT is when epsilon 3 is equal to 0. Sorry, when epsilon 3 is equal to P3. Well, what do you get? So you get an E squared. You get a P3 squared minus 2 P1 dot P3. And then you get a P4, let's say minus 2 P2 dotted with epsilon 4. And then the denominator Well, good news, that's P3 squared minus 2 P1 dot P3, which cancels the guy in the numerator. So this is E squared times P4 minus 2 P2 dot epsilon 4. Okay. So it's some function of epsilon 4, which is the polarization of the other photon, the one where I'm not trying to check the Ward identity. And it depends on these various momenta. Okay. And likewise, let's compute m sub u. So we get an E squared out front. That first term is now right here. That's a P3 squared minus 2 P1 dot P3, or P2 dot P3 times P4 minus 2 P1 epsilon 4 divided by the denominator. You can now see why I chose to write the denominator in terms of P2 and P3. You get a P3 squared minus 2 P2 dot P3, which cancels the corresponding term in the numerator, and you get E squared times P4 minus 2 P1 dotted with epsilon 4. Okay. So you add it all up together, and you get something proportional to E squared. You get a factor of 2. Okay. So you get a P4 from mu and mt, and you get a P1 from one of them and a P2 from the other. You get 2, the electron charge squared, times P4 minus P1 minus P2, all dotted into epsilon 4. Okay. Now, the first thing that you should note about this is that it's not 0. Right? Even if, I didn't use the fact that P4 dot epsilon 4 is equal to 0, but even if I used that, I still am left with this term here. Okay. So this is not 0. Okay. So can anyone tell me where I've gone wrong here? Yes. Yes. So as I promised earlier, the Ward identity is only going to be true if you include all of the diagrams up to a given order in perturbation theory. So we've forgotten about the Seagull diagram. I'm going to just call it the Seagull diagram from now on, from forever on. Okay. The Seagull diagram, let's call it M4, there it is. So this is P1, P2, P3, and P4. Okay. Now, it doesn't actually depend on any of those momenta. You just get 2I times the electric charge squared, and you get, what do you get? You get G mu nu epsilon 3 mu epsilon 4 nu, so otherwise known as 2I E squared epsilon 3 dot epsilon 4, which tells me that I missed a factor of I somewhere up to here. And indeed, there's no factor of, where's my factor of I? Ah, there was an additional factor of I here, which I forgot about, so I should factor that out here. Okay, much better. Good. Sorry about that. If they assigned me this class earlier in the day, I wouldn't make nearly as many mistakes. But they assigned it to me late in the day, so now I have an excuse for all of the mistakes that I make. Okay, so there is that. Okay, so what does that mean? That means with epsilon 3 proportional to P3, we can now go ahead and try and check the Ward identity, and you get the U channel, the T channel, and the 4-point interaction. And what do you get? Well, this first term was up here is 2e squared times p4 minus p1 minus p2. And the second term gives you 2e squared times p3 dotted in with epsilon 4. So altogether you get 2e squared times p3 plus p4 minus p1 minus p2 dotted in with epsilon 4, which vanishes by the conservation of momentum. By the fact that all of these diagrams conserve momentum. So, I mean, this is a kind of remarkable thing here. So, remember that the 4-point interaction, M4, the Siegel diagram interaction, only arose because the term A mu, phi bar phi, was necessary for gauge invariance. Naively, when we coupled the gauge field to the current of a charged scalar field, the U1 current, the charge rotation current, you only had an A mu, J mu term, which gave you that 3-point vertex between an electron, a positron, and a photon. Okay. We now see, okay, but we saw that that wasn't gauge invariant. We made a big fuss about it, and we learned that the only way to fix that up was by adding this additional 4-point term. And you can see that it's precisely that 4-point term that's coming in to save the day and give us the Ward identity. And the precise coefficient of that 4-point function was important. Okay, the fact that its coefficient was e squared rather than e meant that it came in at the right order in perturbation theory. The fact that there was a factor of 2 was important. All of this stuff was important. Okay. So this is really a general lesson. First of all, that Ward identities often follow from cancellations among many Feynman diagrams. And in particular, this really points towards a kind of general flaw or shortcoming of the approach to quantum field theory based on Feynman diagrams, which is that Feynman diagrams, although they're incredibly useful for doing calculations, often obscure the symmetries or various sort of fundamental properties of scattering amplitudes. So in general, if you have some sort of physical system with a symmetry, then you want to exploit that symmetry to the maximum extent possible. And we see now that there's an extent to which the Feynman diagrams don't do that. Okay? And that, you know, if I were working not at tree level but at a higher order, there might be hundreds of diagrams. And the Ward identities, the fact that the answers are gauge invariant, will only be apparent when you sum up all of those diagrams and look for all of the cancellations between them. This really means that Feynman diagrams, in some sense, are very inefficient. Because when you calculate Feynman diagrams, you're calculating more than you need to, because you're calculating all of the stuff that has to cancel out at the end of the day. Okay? So one of the things that people very often try and do, sort of in sort of current research, is develop alternate techniques for calculating in perturbation theory that make symmetries like Ward identities explicit at each step, intermediate step in your calculation. This means that you're not doing things like calculating tons and tons of Feynman diagram, pieces of Feynman diagrams that are only going to cancel out at the end of the day. Okay. Any questions on this? Yes.
I'm confused with the setting of the positive. Is there any way of
Okay. Would you be happier if I said with epsilon 3 replaced by P3? Because what was the point of the word ident? Okay. Remember, what do we do with an epsilon? What we do with an epsilon is we contract it with an amplitude in order to give you an amplitude to scatter into a particular polarization state. Okay. So, if this scattering matrix vanishes when you contract it with the momentum, then that means that if I just made the formal replacement where I replaced epsilon by k, the answer should be 0. Okay. So I'm not saying when epsilon, it's not that I want to set epsilon equal to P3. I want to kind of just replace in all of my formulas epsilon 3 by P3, and then I should get 0. Okay. Is that satisfactory? Good. Okay.
Another question.
Yes.
I think we don't set the momentum of Sarah Focus
Yeah.
just for
Yeah, yes. So I'm gonna use that. Okay. So let's get to that. Okay. We also learned another general lesson, which is that Ward identities are true even if the external photons are off shell. So that P3 squared and P4 squared are arbitrary. And in particular, I had to make no assumption about, say, epsilon 4. So what does this mean? This means that I could actually use this Ward identity to help me prove statements about photons that are internal to the diagram, that is to say virtual photons. If I were considering a process with a virtual photon, then it could be off shell, it may not, its momentum could not square to 0, okay? But I can still say things about this. And in particular, it's precisely this fact that one can use to argue that the results of these scattering amplitudes are gauge invariant when one considers the dependence on the R psi parameter in the propagator. So remember, that pi mu nu is proportional to g mu nu minus this additional term that depended on the parameter psi and was proportional to p mu p nu. Okay. So let's imagine, but we want our results at the end of the day to be independent of this parameter psi. Okay. So pi has a psi-dependent term which must cancel in any diagram. Or, to say that a little bit better, in any individual diagram, the psi's might not cancel, but when you add up all the diagrams, the result's going to be independent of psi. So, consider the following 3 diagrams. Okay, so let's consider the case where we have an electron and a positron coming in. They create a pair of photons, okay? But instead of those photons, going off and being observed, they participate in some other sort of process, okay? So there's some other stuff going on in the Feynman diagram there. Could be other loops, could be anything. Okay. Now, let's say we want to integrate over this loop momentum, okay? And I'll take the undetermined momentum to be this guy right here. Okay, so that's P3 will be the undetermined momentum. So then, for example, P4 is going to be determined by P3. And P1 and P2. So here's P1 and P2 as usual. Okay. Now, that means that when we integrate over P3, we have to consider the case where P3 doesn't square to 0. And we'll need to include a propagator associated with P3. So pi mu nu for this undetermined momentum associated with P3. So pi mu nu for this propagator right there has a term that is dependent on psi that is proportional to P3 mu P3 nu divided by P3 squared. Okay. That's this term right up here. Okay. So in particular, it looks just like we have some sort of polarization vector epsilon 3 proportional to P3. And now, if you just had this Feynman diagram here, then that term is just going to be there and it'll be zeta dependent. However, if you add in the following other two diagrams, which correspond to the U-channel and the 4-point vertex. So if you add in a diagram that looks like the U-channel guy, okay, again, those photons are hopping over one another, plus the 4-point vertex, well, what will you get? You'll get exactly the quantity that we computed above, except that P3 and P4 don't square to 0 because they're internal momenta. Okay. They should be integrated over. They might be off shell, but they're virtual particles. Yet nevertheless, we'll have exactly the same cancellation. And so the same cancellation as above will imply that the sum of these three diagrams is going to be independent of our choice of gauge. In particular, if you just imagined summing up this diagram here, and this diagram here, what will you get? You'll get exactly what we called MT plus MU plus M4. In general, that's going to be non-zero. It'll give you some contribution to this process. But the part of it that is proportional to zeta, okay, coming from this propagator right here, is going to vanish precisely because that propagator looks just like a polarization vector proportional to P3. So we can see that so not only does gauge invariance imply Ward identities, which are properties obeyed for external photons, but that precisely the same set of cancellations are necessary in order for amplitudes to be gauge invariant, even when you don't have external photons. This is a kind of general strategy that we're going to be using, which is that properties that are true for tree-level diagrams often reflect deeper properties that are true for loop-level diagrams as well. So the tree-level property that we saw, which was the Ward identity, turns into some loop-level property, which is the independence of the diagram under the from the choice of gauge. So I sort of just sketched that a little quickly. I invite you to go through and convince yourself that all of the indices contract in the right way, and this thing really is gauge invariant. If it makes you happy, if you don't like considering general blobs are not fun to consider. you could consider something more, less blobby, I don't know, something like that. Okay. Yeah, so I invite you to go ahead and write down the sum of this guy plus this guy plus this guy, okay, and verify that, without actually doing the computation, it'll be two undetermined loop momenta. You don't want to have to do that integral. It'll be hard. But just verify that the cancellations that we went through before tell you automatically that this guy is independent of the choice of gauge, and in particular of the parameter psi. I mean, it's kind of interesting that when you compute all of these Feynman diagrams, you end up computing all of this unnecessary stuff that cancels out in the end. Okay? You could say, well, what if we just set psi equals to 1? Then it's not that hard, and there's some extent to which that's true. But I think this does point to the fact that, to some extent, the method of Feynman diagrams is incredibly useful, of course, but is certainly not necessarily the right way of calculating gauge theory scattering amplitudes if you want to make all of the symmetries of the theory completely manifest. It would be like working in a theory that is rotationally invariant but not using spherical coordinates or something like that. Your answers at the end of the day will be invariant, will conserve angular momentum, but that will not be apparent at intermediate stages of the calculation. So in fact, one of the big current hot topics of activity in quantum field theory is developing other diagrammatic techniques that are not Feynman diagram techniques, but are closely related, that sort of preserve gauge invariance at each step along the way. But we're not going to talk about that in this class. Okay, so this is all I wanted to say for now about gauge theories and scalar QED. Next class we'll talk about spinors, about what we mean by a particle and why particles necessarily have spin. Yes, question before we end.
So we could classify our diagrams with respect to the order.
Yes.
The diagrams cancel in particular here.
Well, pieces of the diagrams cancel. I mean, of course, it is not the case that all of these diagrams cancel, but that, for example, these three diagrams, if you sum them together, don't give 0. Okay. Right? But if you took the derivative with respect to zeta, this would be equal to 0. Okay.
So if we classify our calculation here with respect to H bar.
Yes?
Is there anything happening with cancellations and stuff?
Well, sorry, maybe I don't quite understand. I mean,
if we classify our calculation here with
Yeah.
respect to powers of H bar.
you mean powers of E. So powers of E is the same as powers of H bar. I invite you to check that. Okay. We're using E, so we're working in units where E is dimensionless. So I invite you to go back and restore your dimensions, and you'll see that there's a power of H bar there. The loop expansion is the 1 over H bar expansion. So yes, and in order for this to be true order by order in H bar, it's crucial that we have a theory where the coupling constant E is continuously adjustable. If we didn't have a theory where E was continuously adjustable, it's a continuous parameter. So if the theory were somehow only defined when E was equal to 12, okay, well, you wouldn't want E to be equal to 12. That's an awfully big number. If the theory were magically only defined when E was equal to a third, which is what it really is, okay, then you would not be able to work to some finite order in E to verify this cancellation, or at least not unless you got very lucky. I mean, in scalar QED, of course, you could do that, but in some counterfactual theory where E is only defined when it's equal to a third, and indeed there actually are sort of theories like this that don't have freely adjustable parameters, then you can't ever work to finite order in some perturbative expansion. You just have to have something that's true at all orders. Okay? So if you had some, let's say you had some gauge theory, okay, but you didn't have some freely adjustable charges. Instead, they were, just fixed for some reason, and you couldn't make this argument where you truncated finite order. I mean, there are quantum field theories which don't, when we take quantum field theory classes, we're sort of spoiled because all of the theories that we think about have nice perturbative expansions. Okay? But there's no rule that says that every quantum field theory has a nice weakly coupled perturbative expansion. Okay? Yes?
Is there any physical proof like that?
The Ising model is a physical theory. Okay? It's probably the most, yes. So, yes. I would say that, yes. I mean, many theories have no weak coupling expansion. QCD at low energies has no weak coupling expansion. Okay. Still, in QCD, you can still work order by order and verify things order by order because it has a continuously adjustable parameter. Okay. Yes. Yes.
What conformal coupling? So basically it's just a number.
Conformal coupling. Sorry, maybe I don't know exactly what you mean. I mean, if you mean a conformally coupled scalar field or something like that.
From gravity when you actually
Yeah.
had
So yeah.
specific output depending on dimension of the whole thing.
Yeah, I mean, okay. Yeah, I mean, there are certainly special values of parameters that appear all the time in theories. So let me give you another example, which is much simpler than that one. So there are very often special values of parameters where new symmetries emerge. The most interesting one is that if you consider a vector field A, then, although I haven't done it so far in this class, you could consider a massive vector field, okay? So by adding an interaction term that looks like m squared a squared to your theory, and then that theory is not gauge invariant. Okay? In this case, the A has 3 degrees of freedom rather than 2, because there's now a new polarization of A that is parallel to the direction of motion rather than just perpendicular. But precisely when m squared is equal to 0, that state drops out of the theory. And so that's an example. Okay, so I mean, that's not supposed to be, it's a true statement. It's not supposed to be obvious at this point. And so there's certainly plenty of examples where there's special values of coupling constants where new symmetries emerge. Okay. I don't know how that would fall into the characterization of what I just set up here. Okay, I feel like I've gotten sort of distracted from whatever it was I was talking about, which I don't remember. And I'm also 7 minutes over, so maybe I should stop here and I'll see you all on Thursday.